In 1977, NASA launched the Voyager Two spacecraft on a mission to explore the outer planets.
Imagine a lone spacecraft hurtling through the silent void more than 12 billion miles, or 20 billion kilometers, from the only home it has ever known, Earth. Launched in 1977 with a mission expected to last mere years, Voyager 2 has defied every expectation, surviving nearly 5 decades. It carries the golden record, a time capsule of humanity, music, greetings in 55 languages, images of our world, and the blueprint of life itself. This is more than a spacecraft. It is humanity's first messenger into the galaxy, a fragile envoy at the edge of forever. And now, Voyager 2's final transmission has confirmed what we all feared. This is one cosmic story you won't want to miss. Origins of the Grand Tour. In the mid-1960s, while the world's attention was largely fixed on the space race between the United States and the Soviet Union, a quiet but transformative discovery was taking shape at NASA's Jet Propulsion Laboratory, or JPL, in Pasadena, California. It was 1965, and Gary Flandro, then a doctoral student at the California Institute of Technology, working as a summer intern at JPL, made an observation that would change the trajectory of planetary exploration. Using little more than pencil calculations and ephemeris tables, he realized that the outer planets, Jupiter, Saturn, Uranus, and Neptune, were slowly moving into a rare alignment, an event that occurs only once every 176 years. This cosmic arrangement, he recognized, could be exploited to send a spacecraft on a grand tour of the outer solar system. Instead of expending enormous amounts of fuel to reach each planet individually, a single probe could use gravity assists, or slingshots around planets, to gain momentum and alter its path from one giant world to the next. This made the impossible suddenly plausible. At the time, NASA was consumed with the Apollo program and the ambition to land a man on the moon before the decade's end. Yet the implications of Flandro's realization were too important to ignore. If engineers could design a probe capable of surviving a decade-long journey through deep space, it could revolutionize humankind's knowledge of the outer planets. Without the Grand Tour trajectory, such a mission would have been far too costly and time-consuming, requiring separate launches to reach each planet. With it, a single craft could achieve in 12 years what might otherwise take 30. The opportunity was fleeting. The alignment would not occur again until the 22nd century. The clock was ticking. As the 1970s approached, the vision began to take shape. Engineers at JPL and scientists across NASA started planning what was first called the Mariner Jupiter-Saturn mission, initially conceived as an ambitious expansion of the successful Mariner program. But the potential revealed by Flandro's alignment inspired larger ambitions. Why stop at Jupiter and Saturn if the same trajectory could, with careful navigation, carry a spacecraft to Uranus and Neptune as well? The concept of the Grand Tour was formally studied, and though budget constraints forced NASA to scale down the original proposal for 4 spacecraft into just 2, the dream survived. In 1972, Congress approved funding for the Voyager program. Launched just weeks apart in the late summer of 1977, Voyager 1 and Voyager 2 were built as twin spacecraft but given slightly different missions. Voyager 1, launched on September 5, 1977, was placed on a faster trajectory to fly past Jupiter and Saturn and then head out of the ecliptic plane. Voyager 2, launched earlier on August 20, 1977, took a longer, slower path, one that would allow it to take advantage of the full planetary alignment. It was Voyager 2 that became the true embodiment of Flandro's Grand Tour. While Voyager 1 completed its encounters with Jupiter in 1979 and Saturn in 1980, Voyager 2 continued on, bound for the uncharted territories of Uranus and Neptune. Voyager 2's passage by Jupiter in July 1979 delivered the first hint of the extraordinary science the Grand Tour would produce. It observed the planet's turbulent atmosphere in unprecedented detail, captured images of its faint ring system, and revealed the volcanic activity on its moon, Io, eruptions so powerful they reshaped understanding of geology beyond Earth. At Saturn, which Voyager 2 reached in August 1981, It recorded the planet's intricate rings and discovered new moons. Yet even these discoveries were a prelude to what made Voyager 2 unique. The voyage of Voyager 2. On January the 24th, 1986, Voyager 2 made its closest approach to Uranus, passing within 81,500 kilometers, or 5,600 miles, of the planet's cloud tops. This was a moment of historic significance, the first and only time a spacecraft has flown by Uranus. The data shocked scientists. Uranus, long thought to be a bland and featureless ice giant, revealed a tilted magnetic field unlike anything seen before, offset from the planet's center and tilted 59 degrees from its axis of rotation. Voyager 2 also captured images of the planet's faint rings and discovered 10 previously unknown moons, dramatically expanding knowledge of the Uranian system. Even more puzzling was the planet's temperature. Voyager 2 measured Uranus's atmosphere as the coldest of any planet, plunging to minus 224 degrees Celsius or minus 371 degrees Fahrenheit. These findings upended prior assumptions. They also proved how little we knew about the ice giants.
Spin of a planet is the all-important process or thing that organizes weather.
3 years later, Voyager 2 achieved another first. On August 25, 1989, it swept past Neptune, coming within 4,150 kilometers, or 3,080 miles, of the planet's north pole. No spacecraft has visited Neptune since, making Voyager 2's data still the definitive reference for the planet. The flyby revealed Neptune as a surprisingly dynamic world, dominated by supersonic winds reaching 2,100 kilometers per hour, or 1,300 miles per hour, and home to massive storm systems like the Great Dark Spot, a vortex nearly the size of Earth. Voyager 2 also discovered 6 new moons and confirmed the presence of faint rings. Perhaps most astonishing were its images of Triton, Neptune's largest moon, where it found geysers of nitrogen erupting into space, a sign of active processes on a world once assumed to be frozen and inert. By completing flybys of Jupiter, Saturn, Uranus, and Neptune, Voyager 2 accomplished what no other spacecraft had done: a full planetary grand tour. Without Flandreau's insight in 1965, this window of opportunity would have closed for centuries, and humanity would still be blind to the wonders of the ice giants. For a cost of about $865 million in 1977 dollars, roughly $4 billion adjusted for inflation, the 2 Voyager probes have continued to return data for nearly 5 decades. The spacecraft carried 11 scientific instruments, including imaging systems, magnetometers, plasma detectors, and cosmic ray sensors, all designed to operate autonomously across billions of kilometers. Its longevity, far surpassing its initial 5-year mission design, demonstrated the durability of 1970s engineering and the effectiveness of long-range mission planning. Each planetary flyby required precise navigation and timing, leveraging gravity assists to reach the next target. The spacecraft's instruments continued to transmit data long after the encounters. Then came the moment of truth: the crossing into interstellar space. In November 2018, Voyager 2, nearly 41 years after its launch from Cape Canaveral on August 20, 1977, achieved a historic milestone by crossing the heliopause, the outermost boundary of the heliosphere, where the influence of the sun's solar wind is overtaken by the interstellar medium. The heliosphere is essentially a protective bubble, carved out by charged particles, streaming from the sun at speeds of approximately 400 kilometers per second, or 900,000 miles per hour, which shields the solar system from a significant fraction of galactic cosmic radiation. For decades, the precise structure and location of the heliopause remained theoretical, estimated to lie roughly 120 astronomical units from the sun, though it is subject to fluctuations caused by the solar cycle. Voyager 2 crossed this invisible boundary at a distance of about 119 astronomical units, or 17.8 billion kilometers, from Earth, officially entering the vast ionized plasma that fills the space between stars in the Milky Way. This is the interstellar medium. The spacecraft's crossing of the heliopause marked the second such event in human history, following Voyager 1, which entered interstellar space on August 25, 2012, at approximately 121 astronomical units from the Sun. While both spacecraft carried nearly identical instruments, the data they returned revealed surprising contrasts in the nature of the solar boundary. Voyager 2's instruments, including the plasma science experiment, the cosmic ray subsystem, and the magnetometer, recorded a sudden and dramatic decrease in the velocity and density of the outward-flowing solar wind. The spacecraft detected a sharp drop in particle density from roughly 0.002 electrons per cubic centimeter within the heliosphere to about 0.0005 electrons per cubic centimeter in interstellar space. Simultaneously, the intensity of galactic cosmic rays spiked. This abrupt transition challenged prior assumptions that the heliopause would be a more gradual, diffuse boundary, and it provided the first direct measurements of plasma conditions in true interstellar space at Voyager 2's trajectory. One of the most striking revelations was the sharpness and density of the boundary. Scientists had expected a smoother transition between the Sun-dominated heliosphere and the interstellar medium, but Voyager 2's plasma measurements showed a sudden, well-defined interface, with an unexpected spike in the density of plasma from the interstellar medium just beyond the boundary. The plasma density, measured by Voyager 2, rose to approximately 0.08 electrons per cubic centimeter, nearly 50 times higher than the density inside the heliosphere. The temperature of the interstellar plasma was also lower than models had predicted, indicating that the medium is colder and more structured than previously thought. These observations were immediately recognized by NASA and the broader astrophysical community as paradigm-shifting, forcing researchers to refine theoretical models of how stellar winds interact with the galactic environment. Voyager 2's magnetic field readings added another layer of intrigue. The spacecraft detected a change in the direction and intensity of the magnetic field, from approximately 0.0 nanotesla within the heliosphere to around 0.5 nanotesla in interstellar space. Unlike Voyager 1, which recorded a sudden, turbulent and highly variable magnetic field upon its exit, Voyager 2 observed a smoother, more stable transition. This discrepancy highlighted that the heliopause is not uniform, but instead exhibits localized variations influenced by solar activity, interstellar magnetic pressures, and the relative motion of the Sun through the galaxy. These differences demonstrated that the outer reaches of our solar system are far less predictable than existing models suggested. The spacecraft's plasma wave instrument provided further insights into the structure of interstellar space. As Voyager 2 entered the interstellar medium, it detected a series of plasma oscillations caused by interactions between electrons and interstellar magnetic fields. These oscillations allowed scientists to calculate the electron density and the speed of interstellar plasma, a measurement never before possible at such distances. The data confirmed that interstellar space is filled with low-density, ionized gas that is magnetized and moving relative to the solar system at roughly 26 kilometers per second or 58,000 miles per hour. The observation of these oscillations also allowed researchers to estimate the pressure balance between the solar wind and the galactic medium, providing unprecedented constraints on models of stellar wind interactions and heliospheric shielding. Voyager 2's crossing also demonstrated the resilience of decades-old technology. Operating on a dwindling power supply generated by its 3 radioisotope thermoelectric generators, each producing less than 250 watts at launch and decaying over time, the spacecraft continued to maintain its orientation, transmit data, and operate critical instruments autonomously. This longevity allowed for detailed, high-fidelity measurements at a location more than 17 billion kilometers from Earth, an achievement that highlights both engineering foresight and the durability of 1970s space technology. The spacecraft's antennas communicated through NASA's Deep Space Network, overcoming a one-way light time delay exceeding 16.5 hours. Another remarkable aspect of Voyager 2's crossing was the comparison with Voyager 1's earlier data, which revealed that interstellar space is highly heterogeneous. Voyager 1 had encountered sudden fluctuations in plasma density and magnetic field orientation, suggesting a turbulent boundary layer, whereas Voyager 2 recorded a more gradual and consistent environment, emphasizing that the heliopore's structure depends strongly on local conditions, including the influence of solar magnetic cycles, interstellar magnetic field orientation, and variations in cosmic ray pressure. Beyond the scientific data, Voyager 2's entry into interstellar space carried symbolic and philosophical significance. For the first time in human history, an object built by human hands crossed into the medium between stars, a region untouched by earthly influence. But that's not all. The cosmic hum. In late 2018, shortly after Voyager 2 crossed the heliopause into interstellar space,
NASA's Voyager 2 crossed into interstellar space in November of 2018.
Scientists began analyzing the data from its plasma wave subsystem, or PWS, an instrument originally designed to measure oscillations in the density of charged particles in the outer heliosphere. What they discovered was both unexpected and unprecedented: a constant, low-frequency oscillation emanating from the plasma of interstellar space itself. Unlike the violent, chaotic solar wind interactions inside the heliosphere, these waves were subtle, almost imperceptible, yet persistent, resonating like a cosmic hum. For the first time, humanity had captured the actual sound of interstellar gas. The phenomenon occurs because interstellar plasma, a diffuse mixture of electrons and ions, naturally oscillates when disturbed. These oscillations generate electromagnetic waves detectable by instruments like the PWS, which measures the voltage induced by moving electrons. In Voyager 2's data, the plasma waves were remarkably steady, with frequencies typically in the 2 to 3 kHz range, corresponding to electron densities around 0.06 to 0.08 electrons per cubic centimeter, consistent with measurements of the interstellar medium's density taken during the crossing. The steadiness of these oscillations surprised researchers. Previous theoretical models had predicted turbulence at these distances due to the interaction between the solar wind and the galactic medium, yet Voyager 2 found a more ordered structure, a nearly harmonic vibration permeating the plasma. It was not a chaotic, stormy environment, but a calm, resonant field. Voyager 2's discovery echoed similar observations made by its twin, Voyager 1, in 2012, which recorded plasma wave frequencies corresponding to slightly lower densities, around 0.05 electrons per cubic centimeter, indicating that the interstellar medium is heterogeneous but possesses regions of remarkable uniformity. By comparing the two datasets, scientists realized that the interstellar plasma behaves more like a conductive fluid with long-range order than a turbulent, chaotic gas cloud. This understanding was crucial for modeling how the Milky Way's plasma interacts with stellar winds, cosmic rays, and magnetic fields. It also allowed researchers to estimate the speed and pressure of interstellar plasma, revealing that the medium is moving relative to the Sun at approximately 26 kilometers per second, or 58,000 miles per hour, a motion detectable through Doppler shifts in the plasma wave frequencies. The so-called cosmic hum is fundamentally tied to the electron plasma oscillation frequency, which depends directly on the electron density. By measuring these oscillations, Voyager 2 not only confirmed the density estimates of interstellar space, but also provided the first real-time, direct observations of the dynamical behavior of galactic plasma. Before Voyager, scientists relied on indirect measurements, such as stellar scintillation or radio wave propagation, to infer the presence of interstellar plasma. Now, for the first time, they could hear the medium itself. One of the most striking features of the hum is its constancy. While interplanetary space is dominated by the Sun's 11-year activity cycle, manifesting as fluctuations in solar wind density, magnetic storms, and energetic particle flux, Voyager 2 recorded a stable, near monochromatic oscillation in the interstellar plasma. This indicates that beyond the Sun's influence, the plasma exhibits long-range order, with density waves propagating across millions of kilometers without significant disruption. The constancy of the signal also implies that the interstellar medium possesses self-organizing properties governed by the interplay of magnetic fields, electron pressure, and plasma currents. Scientists liken this to a cosmic-scale musical note. This constant faint vibration acts as a natural barometer, revealing how the heliosphere, the Sun's protective bubble, interacts with the surrounding galaxy. Subtle modulations in the hum captured ripples caused by the Sun's expanding and contracting magnetic influence, while localized fluctuations hinted at denser plasma currents, remnants of ancient supernovae, and magnetic reconnection events. For the first time, humanity was not inferring the interstellar medium from distant starlight, but directly listening to it. The hum's detection also reflects the remarkable durability of Voyager 2. Launched in August 1977, the spacecraft runs on 3 radioisotope thermoelectric generators, which have been steadily losing about 4 watts of power per year. To preserve its core instruments, engineers at NASA's Jet Propulsion Laboratory have gradually shut down heaters and subsystems. Yet, even at more than 18 billion kilometers from Earth, transmitting across a 16.5-hour one-way communication delay, Voyager 2 continues to send detailed data through NASA's Deep Space Network. Its plasma wave system, never designed for interstellar conditions, still measures plasma densities and wave frequencies, proving that the aging probe is not just surviving but actively exploring. Beyond the science lies Voyager 2's symbolic resonance. The golden record it carries, curated by Carl Sagan's team, includes 115 images, greetings in 55 languages, music from Bach to Chuck Berry, and natural sounds like whale song and thunder. Though the odds of it being intercepted by extraterrestrial life are vanishingly small, its presence transforms Voyager 2 into both a time capsule and a cosmic ambassador. The spacecraft's planetary flybys between 1979 and 1989 shattered assumptions of inert outer worlds, revealing Jupiter's volcanic moons, Saturn's dynamic rings, Uranus's tilted axis, and Neptune's supersonic winds. Its 2018 crossing of the heliopause showed that the solar system's edge is abrupt, violent, and structured. Voyager 2's faint signals today remind us of human fragility and resilience. A 1970s machine built for a 5-year mission still whispers across the void. Long after its power fades in the 2030s, the spacecraft will endure as a silent messenger, bearing humanity's voice into the infinite night. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.